I want to talk about some of the efforts that we've been working on for microscope control, hardware control in general in the Python, ecosystem. I'll certainly present Napari Micromanager, but the talk really isn't focused on integration with Napari per se. It's more just about really, it's about efforts to bring, the best of Micromanager to a pure Python C environment and keeping Java out of the loop in as much as possible. And I'll talk about why I think that's important. But that's really sort of the summary for the day. I'll present these sort of 4 libraries that are all in the PyMM Core Plus organization on GitHub, and explain, the rationale for them, why I think, why they've sort of evolved, and where I see them all interacting with each other, with an eye towards, what we were just talking about, with an eye towards using the good parts of Micromanager, because there are many, as well as being able to easily customize and extend the Micromanager facility, capabilities with pure Python stuff, custom device drivers, without necessarily needing to write a C++ device adapter or go into Java or anything like that. So that's really what we're trying to enable. And before I even get started, I want to just mention Federico Gasparoli, who is a postdoc in our group, who has done a tremendous amount of work on what I'm about to show. So I will credit everyone at the end again, but I just wanted to give an immediate heads up to him. Right. So yeah, I decided to start with this slide just because as I was putting this all together, I recognized that most of this really sort of hinges on wanting to in some way incorporate Micromanager. There's a couple things that we've done here that I see as truly independent of Micromanager, and just sort of a schema or an interface or a framework for just describing a sequence of some sort of events on a microscope or a similar device that needn't necessarily need Micromanager. But a lot of what I'm talking about here really sort of begins with Micromanager because, of course, it comes with a lot of functionality built in. So I'll just remind everyone that Micromanager is open source microscopy software. It's been around for a couple decades now. Nico Sturman is really the driving force behind it, with a number of other really important people along the way who have just done a real heroic effort to bring open source microscopy control to bioimaging, right? So I want to kind of give, I guess, a tour of the ecosystem as I see it, and motivate sort of why we are working on some of the things we're working on. I think there's actually a fair amount of kind of misunderstanding about what Micromanager is at its core, because of how it is, because of the Java interface that most people use it through, right? So I think most people kind of have a conception that Micromanager is a Java program, and the GUI is, the graphical user interface Micromanager is a Java program, but the vast majority of the real critical important functionality is actually written in C++ and doesn't need Java at all. So down here we have, I'll sort of be building up a chart of how things interact, but MM Core is the heart of Micromanager. It's written in C++, and it controls your devices via device adapters. So basically, MM Core defines a C interface that anybody can implement a device adapter for. So basically, device A might write a device adapter that speaks to the firmware or the device driver directly. So basically, you've got MM Core controlling a number of these devices. Each of these devices implement an interface that essentially controls one device. So that's sort of the basic core functionality of Micromanager, is this underlying C++ library and a whole host of device adapters. And this really is, when we talk about like moving away from Micromanager, in as much as people think about that, this is really the gold. This is the bit nobody wants to lose, because there are dozens of device adapters written for, the vast majority of common commercially available devices. Not all, of course, and that's an important thing to discuss as well, but this really is a gold mine of stuff. So what people are usually familiar with and what we tend to think of as Micromanager is MM Studio. So Studio is a Java-based GUI application. And it kind of integrates with ImageJ, as most people know. So you see the ImageJ program, and then a separate window, which is Micromanager, and that is basically the Studio GUI. It is controlling the C core via a Core J wrapper. So Core J is a library that is essentially a Swig wrapper on core. So Studio talks to C++ via this intermediate layer of Core J. So again, at the base, it's still C++, but when you're interacting with the graphical user interface, that's where you need the Java. I will also mention that the multidimensional acquisition engine, the thing that lets you acquire 3 channels for n time points and z stacks, etc., and build up a complex multidimensional experiment, that was originally actually written in Clojure, not Java. So what's sort of interesting and complicated here is that as soon as you want to start to do complex things, there's been a little bit of a the ecosystem is a little bit frazzled, I guess, due to lacking this kind of in C, right? There is no C++ acquisition engine. So we can't just all agree to kind of use the same lower level C++ acquisition engine, because it doesn't exist. They made one in Clojure for the original Java application, and there are 2 other engines I'll mention today that run these more complicated experiments. But this so far is kind of the main picture up until now that I think most people are familiar with. I will mention that in the Python world, there is and has been for quite a long time now a library called PyMMCore. This is a Swig wrapper as well for MMCore, so it's analogous to Core J, but for Python. And Swig, for those of you who don't know, is just one of these foreign function interface libraries. It's something that wraps a C library or a C++ library in a Python API, so you can call it directly. So PyMMCore lets you call out to the C++ and directly control that without needing Java at all. So that has been sort of a nice way to sort of directly control this API for quite a while. Micromanager is something that many of you are probably familiar with. It's a Python library that came out a couple of years ago that lets you sort of completely control the Java application from the Python side using inter-process communication. So the way this was designed was essentially to add a couple layers on the Java side, so that they're running a ZMQ server. ZMQ is it's a messaging inter-process messaging server. So essentially, now what you've got going on is in Python, you've got Micromanager running in a Python process. And when you send commands via Micromanager, it serializes those commands to a little message and sends that across to another process where there's a server running, and that server deserializes that command and talks to Core J and an acquisition engine. So they wrote a new acquisition engine also in Java here to control Core J, which in turn controls the C++ core library. So essentially, it does require a Java virtual machine and a ZMQ server, but by doing that, it actually is, the real nice thing here is that it allows you to use all existing Micromanager plugins. So for instance, we have a DieSpim, and DieSpim uses a Micromanager plugin to control it. And if you wanted to control that via Python, this would be a great way to do it. But like I said, it is essentially a Python API to control the Java application. What we really want to do for many of our applications is kind of take Java out of the loop. As wonderful as all those tools are, there are times when you'd like to just sort of be in a pure Python C environment and more directly interface with Core. And as I said, PyMMCore exists for that, and it is great, but there's some rough edges and some stuff that you might be wanting for a sort of mature Python ecosystem. And so that is most of the stuff that we have built on top of. Right. So again, PyMMCore Plus is part of the libraries we've written that aim to take Java out of the loop and build sort of a complete ecosystem on top of this. The reason we want to do this is it makes it easier to install anywhere, so you don't need a Java virtual machine. Not that that's that hard to spin up, but it fundamentally requires a multi-process sort of communication. So it's simpler if we can take that out of the loop. It's easier to install it anywhere if you don't need Java. It makes this much easier to integrate with Python-only device drivers. So if you have custom device libraries, like we were talking about for your fluidics, and you want to just sort of stay in pure Python and integrate that sort of in an incremental or partial way with some stuff going on in Micromanager, then it's nice to sort of keep Java out of the loop there. And of course, if everything's in Python, it makes it easier to integrate with pure Python libraries like Napari. So yeah, I'm going to focus on these 4 libraries today, and tell you what each of them does. I'll pause there. Actually, I mean, we can certainly do all the questions at the end, but I'll just pause briefly in case there's any questions about how the ecosystem puts together. And otherwise, I will keep going. So I'll let you can just holler at me if there's anything in the chat, or people can unmute themselves and interrupt me. That's fine too. All right, so yeah, I want to kind of step through. That was the overview, and I just kind of want to step through them now and give you like a little more detail on each one. So as I said, at the root of all this is Core down here. So Core and devices. This is the C++ code at the core of the Micromanager project. And it's got a ton of these device adapters that control lower level drivers, which in turn control the hardware. And this is the real gold mine of device adapters that already exist. Core, as I mentioned, are Python bindings to that C core. So this wraps it in a Python wrapper and allows direct control. So you would use this as shown down here. You would import Core. You would make an instance of the CMM core. And so now this is a Python object that is directly calling and controlling this C native library. And you have access to the full core API. So we can set device adapter search paths, load system configuration, snap image, get image. And this is a rather extensive API, so it can be overwhelming at times. And I'll mention on the documentation side, one thing we've been trying to clarify with that as well. But suffice it to say that with Core, we're in the door, right? We've got pure Python C access to all of these things, and we're off and running. It doesn't mean everything is easy yet, but we're in the door. So Core Plus was essentially a convenience layer on top of Core that is where I decided to start putting improvements, essentially. Like basically Core itself is a thin wrapper. It probably should remain a thin wrapper. It's not really the place where you want to put all kinds of custom APIs and build on functionality, because it really just is a mirror of this lower level C library. And so unless you're actually directly implementing it in C, I think that Core should stay a thin wrapper. And so that is why we focused on putting the stuff I'll tell you about in this Core Plus. So the primary object really is just a subclass of the main object in Core. So this CMM Core Plus is the main object in this library, and it is a subclass of CMM Core with a bunch of overrides and additions. I have more on the next couple slides, but the summary here is that it implements better observer pattern for connection of callbacks. So if you want to spy on the state of the microscope, the core object, and then call functions in response to various events, it implements a sort of more familiar pattern for that, either using Qt or Signal, another library for the observer pattern, which is something connect my callback, and then when that thing happens, your callback gets called. There is a Python acquisition engine. So as I alluded to before, we have the Clojure acquisition engine. We've got another one written in Java now. And unfortunately, that the lack of there being one in C means that if we want to keep Java out of the loop, that means we have to redo this. I'm actually sort of glad we did it, because it has ended up being a real nice pattern. I'll talk about it later, but so we do have basically an engine here to execute a sequence of events to set up the hardware in some state and then do some event and then iterate, you know. And then lastly, there are some sort of niceties and APIs just for making it a little bit more Pythonic and nicer to work with than PyMMCore itself is. So just an example of that, when I talk about convenience APIs for working with core, if any of you have used PyMMCore, you'll know that it, very much looks like a C library. So for example, if you had a core object and you wanted to say, tell me what the FTSE configuration means, then you might write some code like this. You would say, get me the config data for the channel configuration group and the preset named FTSE. And then you would have to, for I in range config size, get the setting, and from that setting, get the device label, get prop name, get right. Very straightforward, but a little bit verbose. And in many places throughout the code, we can sort of, by using subclasses that implement sort of magic methods, Python's standard sort of dunder methods, we can create a much more sort of Pythonic interface with iterators and mappings and sequences that just kind of behave more like you would expect in a Python world while still being subclasses of PyMMCore. So, it won't break any of your usage here, but you can sort of opt into a cleaner API. There are these event connections and callbacks. So the core object gains this events object that has a number of things you can connect to. For instance, exposure change connect. So here is a function that whenever the exposure changes, we would like it to be called with the name of the device and the new exposure. So for instance, if you did that and then you ran mmc set exposure, this function would get called and it would print exposure changed for camera. That's the name of the device to 100, the new exposure. PyMMCore itself does have a callback system, but it makes it very hard to connect multiple callbacks to certain events. And it's very easy to kind of obliterate all your connections when you try to connect a new one. So this essentially makes one connection to the root callback system and then adds a layer of convenience that is much more like what you are likely to see in the Napari community or just any kind of Qt and or Python-based event run loop. So that's that. Now, as I said, there's also a multi-dimensional acquisition engine. The way this works is with this run MDA method. I will talk about this object more in a bit. This is from useek schema, one of the 4 libraries I'm mentioning today. For now, I will just mention that it is a declarative way, essentially, to define a sequence of events. So it sort of looks obvious here. I'm setting up a sequence with a couple channels. In one of them, I'm customizing the exposure, and the other one, I'm just calling the channel. I've got a time plan where I'd like to take 5 loops with an interval of 2 seconds, and so you get the point, right? And this now will accept that object and execute that experiment in a separate thread. And you can bind callbacks to things like whenever a frame is ready, an image is ready, to either say display it in a viewer or save it or something like that. Right. And yeah, a lot of improvements to the developer experience. So the docs that are linked here, there's a big page here that sort of shows you, I think it's even easier kind of look through this than the CMM-core docs themselves, but you'll also see a plus sign where we have overridden the native implementation to customize the behavior a little bit, to improve it. And there will be an explanation as to why we overrode it, or you might see a little sparkle emoji, which means that this is something that only exists in CMM-core Plus. So we have added a couple things and we've overridden a couple things, and they're all sort of clearly delineated on this page. And then this is sort of not a big deal, but something I'll mention. There is a command line interface. This makes it easy to install the device adapters to actually just run a full-on experiment. If you can give it the configuration to your Microscope config and an experiment file and just fully run the experiment without a GUI. but this is sort of experimental. So that really is the heart of PyMM Core Plus. Basically, you know, it's this convenience layer providing event management, an acquisition engine, and an attempt to just generally improve the user experience. So on top of that, there is PyMM Core Widgets. So this is a library with a set of Qt-based widgets that are basically a view onto the PyMM Core Plus model. So you can think of these as widgets that will either just tell you the state of your microscope or control your microscope in a composable way. So the goal here isn't quite to, the goal here isn't quite to fully reconstruct an application. It's to give you a set of components that you could use to build your own customizable user interface. If you didn't need the full Napari Micromanager, which we'll talk about in a second, this here would give you a set of widgets, like, for instance, you know, just a snap button that whenever you hit snap will call core snap image, or live, which will call core start continuous sequence, right? There is a device property browser. There is a multi-dimensional acquisition setup, you know, camera ROI, config preset. So all the stuff you're sort of used to in the MM Studio GUI. So that really is the way I think of this, as PyMM Core Widgets is essentially the equivalent of MM Studio in the Java world, in the Python world, right? So MM Studio, again, is the Java-based GUI that controls the C underlying core via MM Core J. This is all the stuff that we know and love from Micromanager. PyMM Core Widgets essentially tries to re-implement most or all of those in Qt in Python, controlling the core via PyMM Core Plus and staying in Python and C++. Yeah, and most of those things are there ready to go. That is what widgets are. And that brings us to Napari Micromanager, which essentially is itself not tremendously complicated. It is essentially an opinionated arrangement of these widgets with the important events connected to the Napari viewer. So for instance, as you're running the multi-dimensional experiment, it will be emitting events, frame ready, etc. And Napari Micromanager basically connects those events to callbacks that populate the viewer with the next image, build up your Z-stack, and let you just kind of monitor your experiment as you're going. And this is somewhat recent. It's, of course, changing all the time. Federico is always sort of coming up with the newest and best arrangement of widgets, but in general, it looks something like this. So we definitely take heavy use of the doc widget kind of arrangement. So there's a toolbar at the top that gives you quick access to many common things. You got your config to load your microscope config. You can change your objectives, change your channel, change your exposure, hit snap, go live. This will open up property browser or some illumination widgets, stuff like that. You've got your shutter control here, presets, and a multi-dimensional acquisition thing here. So you can set up your how many channels, Z-stack, positions, time, grid, and click run. And I will show you a little video here. I might skip through some of this, but just this was taken a while back when the GUI looked different, but just to give you a sense. So here is the device property browser that is very familiar if you've used Micromanager. So you just have all your devices and you can actively control their settings. There is a pixel size calibration, which is, of course, going to be important if you care about the size of anything. Right. And so here's an example of the, let me pause this. So again, if you haven't used Micromanager arranges different channel configurations as config groups, right? So you could say, I have a config group called channel, and in that I'm going to have my dichroic, my emission filters, and for each preset in this group, I want all of those devices arranged in a different configuration. And so you can add a preset here. These are the various properties that are controlled by this. And on the right is the specific setting of that property for this preset. So Federico here is making a new one called bright field, and he's just saying, when I'm in bright field, I want you to be using this filter. This is the same thing you could do in Micromanager. It's just in Python. And then he chooses that channel, goes live, and he can use the layer controls to get continuous auto scaling. And now he's moving the joystick on the microscope, and we're off and running. This, I think, now is going to be an example of sort of illumination, right? So point being, we have sort of pretty good complete control of most hardware as you would in Micromanager. Changing the exposure time, cropping. I think he's going to crop down to, a smaller subset, go live again. Finally here, I think we've got, what do we got here? Various cool auto shutter functionality that Federico implemented. This is setting up a multidimensional acquisition. This is an old GUI, but here he's setting up a couple points. So he's made 2 points in the, let me pause. Oh. Yeah, so add a point, add another point, and go up to Z stack, add a Z stack. And now as we hit run, you can see that the Napari window has sort of made a new layer called experiment whatever, and is populating your various dimensions with the dimensions of your multidimensional position. All right, so that is Napari Micromanager. Now, I haven't talked much about USeek schema yet, but it's really important to how all these things kind of work together. And let me tell you about it. USeek schema is essentially it's a specification. It's a implementation agnostic schema for describing a microscopy experiment. And by experiment here, I simply mean a sequence of events. So the goal here is to provide a specification and some Python utilities for event objects that can be consumed by any sort of microscope acquisition engine. Obviously, the first implementation is a Micromanager-based implementation, but it was as we were sort of looking at what MM Studio did in the Java world and what Micromanager was beginning to do or is doing in Engine J. Everybody kind of makes their own internal event object, and they're all very similar. And I just wanted to step back and say, let's define what this thing is. And by doing so, the hope is to encourage interoperability between various efforts. So you could say, if this engine implements support for the USeek schema, then you can execute the same experiment you did. You can swap engines pretty easily. That's, of course, a far off hope at this point. But USeek schema is just is an opportunity to sort of step back and just say, what is this thing, without caring about exactly how we're going to drive it. The how happens in PyMM Core Plus, but it could happen anywhere. So this dotted line with a question mark is meant to sort of show that if we did implement a C++ based acquisition engine, it could also implement support for USeek schema, and I would like to see that sort of thing happen. So basically, there's really two main objects in USeek schema. There is the event object itself. I'll show you, of course, what it is right now, but I will also say that this is definitely an opportunity to solicit feedback. I don't mean this talk right now. I just mean this library is a place to discuss this schema. And if you find it somewhat useful, but it's just missing something that you would fundamentally need to represent your sequence of events, then by all means, don't see this as our everybody must be able to do it with what we have. This is a place to step back and say, what is it we need? And there will be some things that are probably too hard to capture this way, but the goal here is to just make an effort. So the MDA event defines a single event in a sequence. It's got, a channel, maybe an exposure, a position, index in the broader scheme of the experiment. So this might be T0, C1, Z3, whatever. And then there are a few places for customization. So metadata is just any key value pair. So if you were, say, trying to do something combining Micromanager and custom Python acquisition or device driving microfluidics or some Raman scope or whatever. You can put whatever you want in metadata, and then you can customize your engine a bit to look for your custom metadata and do whatever action you need to. Properties is also a list of property or device label, property label, property values. So it's also kind of a key value pair. That one is really geared towards Micromanager, but the assumption is that most things in some way have a label with a device name and some property name and some property value. Maybe it won't be useful in the long run, but that's there. Metadata is the truly customizable spot. So each event now is captured by this kind of object. And what I see an event experiment as is really just an iterable of these. And iterable is important here. I don't want this to be necessarily a sequence of known length. It could be a list of these events, but really the main thing is to recognize that an experiment is a iterable of these events with a potentially unknown duration. And this allows for things like custom event feedback, changing of the experiment as you go, event-driven microscopy. So that's the event object. A higher level object is the MDA sequence. So this is the other main object there. This is a declarative specification for a full multidimensional acquisition. So this lets you say, I've got these channels. This is how I want time. You could have multiple stage positions. Each stage position could have a custom subsequence. So there's a lot of kind of recursion, and you can make it very complex if you need to using recursion, but at its simplest, it looks something like this. And you can define an axis order to say what order you want the acquisition to go in. And the important bit here is that this object is itself an iterable of useek events. So if I call list on this object, and I'm just showing you the first 8 here, it actually pumps out a bunch of these events. And what that means is that we can pass that object directly to PyMM Core Plus's run MDA method. So again, now I'm back in PyMM Core Plus world, and I'm letting you know that PyMM Core Plus implements support for an iterable of useek schema MDA events. So it doesn't have to be this complex sequence object. It could just be a custom list of these events, but this here is an example of how to run a very basic multidimensional acquisition experiment using PyMM Core Plus and passing it an object from useek schema. But as I said, it can get really complex and very customizable. So it doesn't have to be this, our monster object. It can be literally any event, iterable of events. So this is a really nice pattern that Kyle Douglas and Willie Steps helped us come up with, or at least I would say we were happy that this sort of fell into place when their use case came along. So what they really want is queue-based acquisition. So as I said, they don't want to define an experiment up front. They want to have some Python queue into which they will drop events when necessary. So they come from Suliana Manley's lab at EPFL, and they do a lot of event-driven microscopy where, let's say, they're taking an image rarely, and they're looking for an event like a mitochondrial division. And when they spot an event happening using their deep learning models, they want to trigger some sort of change in the acquisition, whether it be imaging faster, zooming in, whatever, right? And so with this pattern here, they can make a queue. They identify some sentinel, some stop object, and this line right here is the magic right here. So by calling iter queue get stop, they're saying, I'm going to make an iterable here of event objects by just popping objects off of this queue until I put onto the queue this special stop object. And without doing anything else, PyMM Core Plus can support that. And now somewhere else in their code, in response to analysis, they just drop events as needed into this queue. And this is all running in another thread now. And we'll just, anytime it sees a new event, it'll execute it. You can code for waits, wait some period of time or something like that. But this now just makes a really nice pattern for event-driven custom acquisition. that provides quite a bit of customization just by having a thread running a thing, watching a queue, but you can also fully customize the acquisition engine itself. This is some code that shows you how to do that. So again, we're going to import CMM Core Plus itself, and down here I've made a core instance. And what I'm going to do is set the engine to a custom object. So what is this? This object here is a subclass of our MDA engine. So MDA engine is the thing essentially that executes the sequence of events. There is a built-in one that will do mostly what you need if you have basic experiment needs. But if you need to, for instance, control devices outside of Micromanager for which there don't exist any device adapters, you don't want to write a C++ device adapter, you don't want to go through Java, this is how you could do that. So essentially by subclassing this here, or implementing any class that implements the engine interface. So there's a defined interface of what engines have to do, and really there's only a couple methods they have to implement. They have to be able to set up an event and execute an event. So setup event receives the next event object that's about to come up, and you can do whatever you want there. You might not need to do anything special at all, or perhaps you've put some metadata in that event metadata key value field that I was mentioning. And here's where, you know, that metadata could control, could contain everything you need to set up custom fluidics, do any sort of device setup you need, or execute it here. So this really is your portal here. If you're familiar with Micromanager's hooks, I guess this would be the equivalent here. We don't really need hooks because we're not serializing and doing a lot of cross-process communication. You have much more direct control here over the core itself. So by just subclassing and overriding various methods as you need, you can completely customize exactly what is happening. So, and so you could be using Micromanager for some events, and other events don't need to use Micromanager at all. You can pick and choose what you want. If you're curious to see more of that, there's an example. Ian, who also works on the library, is using this to drive custom ramen experiments where he has a driver that only exists in the Python world, and he intermixes Micromanager and pure Python in that there. So that's an example of that. That is it. Those are how the libraries are put together, and I'll just summarize it again. So as I said, MM-Core and devices. This is the real heart of Micromanager. This is the C++ library that supports a huge range of devices. A lot of good stuff there that we don't want to lose. PyMM-Core is the swig wrapper around this library that has existed for quite a while and provides direct access to MM-Core. Plus, PyMM-Core Plus is the library. The next four are the things. We did not write these top two. Those are from Micromanager. The next four we did. PyMM-Core Plus is the thing that adds all of these Python conveniences, bug fixes, little things that, you know, we find that would be hard kind of to upstream to PyMM-Core or the C library, but are quite easy to fix in the Python world. Some event connections and an acquisition engine. USeek schema then is the specification for the event objects or a sequence of event objects that the engine or the microscope should execute over the course of an experiment. And PyMM-Core Plus implements support for USeek schema. PyMM-Core widgets is that library of Qt-based widgets that make it easy for you to create a custom GUI. So most of the MM Studio Micromanager GUI is in there, not all. But the point here is this is sort of the building blocks for you to build your own custom Micromanager GUI in a pure Python environment. And then finally, Napari Micromanager is really just an opinionated arrangement of these widgets with events connected from the core object to the Napari viewer so that your viewer is populating with images as you go. So this kind of is the most equivalent, I guess, if you will, to MM Studio in Python. And with that, I will just give a hearty thanks and acknowledgement to the main contributors. Federico in our group has just done a tremendous amount of work on this on all four libraries. Ian Hunt-Isaac also has been doing stuff with us for a while, really driving a lot of cool custom applications with his ramen scope. making sure that this all works in practice. Thanks also, of course, to Nico and Mark from Micromanager. They're great, and Jennifer, the director of our group here in the Nikon Imaging Center. And yeah, if you have any more, if you're interested in learning more, I encourage you to go to the repo, which will point you to the docs for these various libraries.